Okay, welcome. This is a video to help you learn how to graph and analyze constant acceleration motion. In lab, you're going to be dropping carts down ramps, rolling balls down inclines. I drew a little example in the bottom left here. Let's just say a ball is rolling down an incline. As it rolls further and further down, it gains speed. So it's not moving at a constant velocity. It's accelerating. And it's accelerating at a constant rate. Now in lab, you're going to be asked to collect a lot of this data and then to analyze it through data tables and through graphs. This example will be simple. We'll use whole numbers and walk you through how to do that. First, let's say when you drop the ball, initially at time 0, I have some data, distance is 0, it hasn't moved. 1 second later, it rolls 1 meter down. 2 seconds later, it rolls 4 meters down, so it's gone further. It's accelerating. 3 seconds later, 9 meters down. 4 seconds later, 16 meters down. So you can see there's not a constant change in distance. It's gaining more and more distance per second it falls, hence the acceleration. Now, if you were to graph that trend, and you look at its change in position or its displacement on the y-axis versus its time on the x-axis, and you plot all 5 points, you realize those points, 0, 0, 1, 1, 2, 4, 3, 9, and the point 4, 16. Those points are not collinear. There is no line that can be connected through them. But they do, if you look carefully, form a different shape. And in geometry and in algebra, you'll learn that anytime the trend appears to increase more and more, it's a parabolic shape or a quadratic trend. And what I'm going to do is just draw a simple little line connecting each point, just to show you that these line segments connecting each data point appear to be growing steeper and steeper. And if you were to analyze the slope between each set of points, we'll look at the first segment is segment 1, the second segment is segment 2, third segment is segment 3, and the fourth segment is segment 4. You can find very easily the slope for a run of 1 second and a rise of 1 meter. You realize the ball rolls 1 meter in 1 second. That's its average velocity in the first second. Then in the second segment, from time 1 to 2 seconds, that's a run of 1 second. That's a rise of 3 meters. So its average velocity is 3 meters per second. So for a run of 1, you have a rise of 3, whereas previously for a run of 1, you had a rise of 1. Let's move on to our third segment. For a run of 1 second, now this graph rises from 4 to 9. In other words, it rises by 5 meters. So you have an average velocity of 5 meters per second. And finally, in the last segment of time, as you run 1 second across, from 3 to 4 seconds, you rise from 9 to 16 meters, or a rise of 7. You have an average velocity of 7 meters per second. So looking at these slopes, you can see that your average velocity in the first second of time is just 1 meter per second. Your average velocity increases to 3 meters per second in that second interval of time. Then it increases to 5 meters per second, and your average velocity continues increasing up to 7 meters per second. Now, if you look at those slopes, those values, there is now a pattern for your average velocities. It should be obvious. They increase by 2 meters per second in each interval of time. So if we look at that graphically on an average velocity versus time graph, graphing your velocity on the y-axis and your time on the x-axis, then in the first second, your average velocity grew to 1 meter per second. In your second segment, it grew to 3. In your third segment, it grew to 5 meters per second. In your fourth second, to 7. Okay. Now clearly, if you consider these points, they are collinear. These 4 points all all lie on the same line. The slope of that line will always rise 2 units for every 1 unit of run. This rises 2 units for every 1 unit of run, and again, this rises 2 units for every 1 unit of run. So if you consider the slope here, where the slope is measuring a rise as your change in velocity and a run as your change in time, it is a constant slope, and it is equal to 2 meters per second each second. And if you carefully consider that relationship of changing velocity per unit time and meters per second, that is a measure of your acceleration. So, for any accelerated motion, you will find that the distance versus time graph will display a quadratic trend shaped like a parabola, and the slopes of those line segments, which measure your velocity during each time interval, will graph a linear trend on your velocity time graph. And by looking at that velocity time graph, you can determine your acceleration. So if this ball was rolling down this ramp, covering this change in distance per unit time, it was moving at a constant acceleration of 2 meters per second, or 2 meters per second squared.